Okay, good evening. Great to see you all here in-house. Welcome to the 71st meeting of SPWLA here in Bangkok. Tonight we're going to have a presentation from Akshay Jayaram on how to select candidate reservoirs for carbon capture sequestration. He is in the US at the moment, so this will all be done online for him, and hopefully everything goes very well. Just to start,
Hope so.
Just want to thank our sponsors, PTTEP, Scientific Drilling, Emerson, Mubadala, Gaia Earth Sciences, Chevron, and Medco Energy. So special thanks to all of those guys for supporting us tonight. And without much further ado, I will hand over control to Mr. Jayaram, and he can take.
That's good.
So prior to joining NSAI, Akshay held various reservoir engineering positions with ExxonMobil, supporting assets in the Middle East, in Guyana, in Russia, and the Gulf of Mexico. His experience included oil and gas reserve and resource estimation, field development planning, reservoir simulation modeling, well testing, economic evaluation using deterministic and probabilistic methodologies, and experience evaluating reservoirs selected for sequestration projects. So without further ado, I'll hand it over. All yours.
Perfect. Thanks, Andrew. Appreciate it. To conserve bandwidth, I'll stop sharing my webcam, so hopefully that makes things a little bit smoother. But yeah, thanks for having me on to present about how to select candidate reservoirs for carbon capture sequestration. Really honored for the opportunity, and hopefully the presentation is, everyone learned something from it, and we can have a good conversation. To start off, yeah, I work for Netherlands Sewell & Associates. We have two offices in Texas, in the U.S., one in Dallas, one in Houston, where we provide independent petroleum property valuations for clients around the world. But we also do other subsurface evaluations like natural gas storage, and more recently, with the uptick in global interest in net zero and greenhouse gas emission management, a lot of carbon capture sequestration type of projects. Yeah, so basically, I'll go over some of the basics of carbon capture sequestration, and then go into a little bit more detail on how you would select specific reservoirs and which reservoirs would be more favorable for CCS, and what issues to kind of to look for. So just kind of at a high level there, and most of y'all are probably have heard of this in some capacity. The main types of carbon storage are either in depleted oil and gas reservoirs or in deep saline aquifers. They can be both onshore and offshore. And this picture kind of shows, it can be, in a depleted oil field. It could be, in saline aquifers. It really is. There are many places you can store the carbon dioxide, but not every project will be the best. It won't work the best for what you have. So you kind of have to look at where's the CO2 coming from, what type of geology you have. Just a quick statistic in the U.S. specifically, at least, while there's a lot of depleted oil and gas fields, the total capacity of these depleted oil fields is on the order of 200 billion metric tons. but when you get into the saline aquifer space, that number is orders of magnitude larger. You know, on the 2,400 to 22,000 billion metric tons of pore space that's available. So, you know, just a lot more opportunity in the saline aquifer space. Obviously, there's some advantages for sticking with depleted oil and gas fields. There's a lot more data available. You kind of, you know, the size of your tank typically a little bit better. You know, there are more well penetrations, logs, seismic, etc. So the tank is better characterized. But when you get into the saline aquifer space, you may not have as much data, so there's a little bit more uncertainty around those subsurface attributes. Other advantages for depleted oil and gas fields are that they're typically at lower pore pressures because of the production. So that makes it a little bit easier to inject into. But the downside, of course, is the more holes in the ground that you have, there are more potentials for anthropogenic leak points because you have so many penetrations. So you kind of have to take that into consideration, especially on the monitoring side, to make sure that CO2 doesn't find its way back to the surface. Let's see, on the saline aquifers, I mean, if anyone who's drilled any exploration wells can tell you that, you know, they're very prevalent. You'll drill through a lot of water reservoirs, so you know, they're just easier to find. Another advantage is they might be located in places that don't have historical oil and gas activity, like at least in the U.S., you know, on the Atlantic coast or states like Illinois. So there are opportunities for co-location with emission sources and saline aquifers that may not traditionally be in where people look for oil and gas. This again, this is a slide for the U.S., but the point I kind of want to make is that the saline aquifers are, you know, typically very prevalent. So on this left side, you can see in blue, these are all the saline formations in the U.S., and in the red, these are kind of the oil and gas fields. So you can see that the saline aquifers are typically very broadly located and areally very extensive. So just, you know, they're very extensively found, so that there are more opportunities for co-locating emission sources with sinks. This slide, again, still US focused, but I think the point that I still want to make is that CCS isn't something that's kind of new technology, because we've been storing natural gas subsurface for many decades. In this picture here, the orange triangles represent natural gas storage in depleted fields. And the blue dots actually represent natural gas storage in saline aquifers. So we've actually been storing gas in the subsurface in the aquifers historically. So it's not very, you know, the fact that we're doing CCS, I mean, we're switching out the natural gas for CO2. So it's not like it's a very novel in terms of the fact that you're storing gas subsurface. So we have experience in this. So I'll get into more on the reservoir selection and evaluation for CCS. Just a quick slide here. You know, it's not just about the geology when you're looking for good carbon capture sequestration sites. This picture is from the Archer Daniels Midland ethanol facility in Decatur, Illinois, in the U.S. On the left picture here, you can see the location of the facility. The picture down here on the bottom left kind of shows you the different reservoir formations. They're injecting in this Mount Simon sandstone. What they have going for them on this very successful project that's been injecting for over 10 years is that the ethanol facility, which is the source of the CO2 emissions, is located right next to their two CCS injectors, so the CCS1 and the CCS2. And they have very, very good sandstone reservoir that they're injecting in, and their CO2 source is actually very pure. So not only do you have good rock that you're injecting in, good permeability and thickness and aerial extent, the CO2 doesn't have to travel very far. It's located right next to their injection wells. And the CO2 that's produced is actually a very, very, very high purity. So not all CO2 sources should be treated the same. CO2 from a natural gas power plant or a cement production facility may be a lot lower concentration, which would basically require a lot more capital or money that needs to be spent to be able to extract that sufficient quantities of CO2 to make a project successful economically. So this Archer Daniels Midland project in Decatur, Illinois, kind of had all three things going for it. So it was very it was kind of an ideal combination. Go to the next slide. Right, so and you'll kind of hear a common theme as I go through these slides, but what type of reservoir is desirable for carbon capture sequestration? Well, a quick answer is if it was a good reservoir for oil and gas production or development, it's probably likely also a good candidate for carbon capture sequestration. And what I mean when I say that is that the things that you look for in an oil and gas development are, how much oil and gas is there, what's the size of the tank, how good is the rock, is the permeability, high enough to be economic. Is there a good top seal that keeps all that hydrocarbon in place and not leaking to the surface? And these are all things that you kind of want in a carbon capture sequestration project as well. So, porosity, thickness, aerial extent, they all kind of form the dimensions of how much tank do I have, excuse me, how much tank do I have? The permeability, if you have some type of injection target rates that you're trying to achieve, the higher the permeability, the more likely it is that you can put away that carbon dioxide with fewer injection wells. If you had lower permeability, you might need to drill more wells, which means more CapEx spending and poor economics. And of course, when we're trying to inject the CO2 into the ground, we don't want it to come back out. So the top seal is very, very important. How much top seal do you have, and how confident are you that there aren't any leak paths that are going to cause the CO2 to escape? So, I mean, these are kind of the basic things that you need in a reservoir for it to be a good candidate for storage of CO2. But like I said before, these are all things that you may be looking for in a economic oil and gas development as well. Structural complexity can also pose additional challenges. So even if you have good permeability and good porosity and thickness and aerial extent, if it's all compartmentalized or there's a lot of faulting, you may not be able to put away as much CO2, or you need to drill more CO2 injection wells because you'll pressure up individual compartments a lot quicker if it's all compartmentalized and sealed off. So you kind of want simple, less structural complexity type of reservoirs, which again is kind of something you want in oil and gas development as well. Another consideration in these type of projects is the number of historic penetrations that are in the area. So while the historic penetrations in the site that you're looking for can provide useful data on, useful log data and give you more information on the reservoir that you're trying to inject in. Every single penetration into the reservoir is a potential leak point. So the fewer leak points you have, the less risk of CO2 escaping out of your target reservoir, the less monitoring that you may need to have to be responsible for. So it just makes it a lot simpler if you find reservoirs or an area of interest that doesn't have too many historic penetrations. So in the slide here, the pictures on this slide here, on the left, it's from a Red Trail Energy Class 6 permit in the U.S. You can see that in the purple, this is the plume that they're expecting after modeling it in a reservoir simulator of the CO2 plume post-injection. And you can see that these blue dots represent, I think, shallow groundwater wells, and these orange dots represent legacy oil and gas wells. So you can see that they've done a good job at when they're injecting in this RTE10, that the plume doesn't really impact or cover or intersect with legacy oil and gas wells, which makes it a little bit more of a simpler process when you're trying to monitor for potential leak points. On the right here, this is these green blocks are the leases that ExxonMobil bid on successfully in the Gulf of Mexico pretty recently. And what you can see here is they seem to have picked a lot of these leases where there are very, very few historical penetrations. And they're likely doing this because they, if they end up using these leases for carbon capture sequestration projects, they have far fewer legacy penetrations that they have to worry about as potential leak paths. This slide kind of covers the PBT characteristics for CO2, but I'll tie it to how it may impact the reservoir that you might select for CCS. This cartoon on the left, so CO2 is a gas at normal temperature and pressure, but at specific temperatures and pressures, it turns into a supercritical phase, and the density increases greatly, which makes it very favorable for these type of these projects. So you can see how at a certain pressure, so in this case, depth is the proxy for pressure here. So at around 1.5 kilometers in depth of CO2 becomes a supercritical fluid, and the density increases drastically from its gaseous state. So this is great. So below 3,000 feet, you kind of want reservoirs below 3,000 feet in depth, so you can keep that CO2 in a supercritical phase. But in this chart here, you can see how as you keep going deeper, the CO2 density doesn't drastically keep increasing as it did from 0 to 3,000. So it's sort of a diminishing returns the deeper and deeper you go, and what you end up having to do is you'll have higher well costs because you're going deeper into a deeper reservoir. You might need to put an extra casing string. You may have higher compression costs. So you're really kind of looking for these sweet spot reservoirs in this 3,000 to 6,000 range just so that you can, you've kind of maximized your CO2 density to get into the supercritical phase, but you're not paying extra for those drilling costs and potential compression costs. So it's kind of a diminishing returns after a certain depth. So that kind of will factor into your reservoir selection when you're looking for a good CCS candidate. I thought I'd get into some case studies of some CCS projects, just to kind of illustrate some of the issues that you might run into. This case study on the slide is from the Salah project in Algeria. So they were separating CO2 from a produced gas stream and were injecting it on site into the formation that you can see in this picture on the right here. The picture on the left is actually satellite data from INSAR, just kind of showing you the deformation at the surface of the Earth. This is typically in very, very small increments. I think it's in millimeters. So the hotter colors represent more deformation. So basically, they were injecting into the ground, and then you can see the wells here, the KB 503, 501, and the 502, which are the injection wells. And I think you would expect some deformation to occur as you inject into the ground. There is some swelling, but you can see how the 502 well looks a little bit different than the 503 and the 501. It's not just kind of a dome deformation response. It's kind of this bimodal or two-domed response. And so why is that happening? So what actually what they found was that the formation they were injecting in was relatively low permeability, had poor communication to the rest of the aquifer. So what happened was they were injecting the CO2 into the formation. The pressure increased so much that it either created a fracture or propagated existing fractures into the top seal. So this is the lower cap rock, the upper cap rock. So this entire interval is their top seal. So you can see here that a fracture was propagated, and what happened was it caused the ground on both sides of where the fracture was propagated to swell up a little bit. So this is just to demonstrate that while they were injecting CO2 successfully into the ground, the lower perm and the potential compartmentalization and not great communication with the surrounding aquifer kind of caused these type of fracturing to occur, which is never really great when you're trying to keep CO2 into the ground permanently. Now, this still was a success because there was no indication that the CO2 actually escaped. It looks like this fracture really only propagated into the lower cap rock and didn't really penetrate or go through the upper cap rock. So the CO2 was still permanently sequestered in the ground. But these are just things that you may want to consider when you're looking at reservoirs that you want to store carbon dioxide permanently. So in this case, just to recap, they had relatively lower perm and poor communication aerially. So that is kind of what caused this to happen in the Salah project. Geomechanical considerations. So coming back to that Archer Daniels Midland project that I highlighted on the first couple of slides. Here, when you inject into into formations that are at original pressure, you kind of want to monitor for seismic activity or induced seismicity. So let me see if I can. So on the top left, again, this is the inset of where the project is. It's in Illinois in the Mount Simon Sandstone. the way this project proceeded was they initially were injecting in the CCS1 well, and then they started injecting in the CCS2 well. So when they started injecting in the CCS1 well, the perforations, if you can see my red pointer, were kind of lower in the sandstone, kind of closer to the basement, crystalline basement. The Mount Simon sandstone is pretty much this from the, I think it's from the blue line. Oh, it's from the pink line all the way down to the blue line. But you can see that they were perfed in the lower part of the interval. But what they noticed was, so you can see here, CCS1 was from 2011 to 2014. In this picture here, this shows some the microseismicity that they were observing. So these are very low, seismic events. I don't think anything exceeded, a 1.5 on the Richter scale. But you can see how there are a lot more of these light blue dots that are occurring. So a lot more of these microseismic responses from injecting into this interval, which when they started injecting twice as much volume in the CCS2, slightly up further offset from the crystalline basement at the bottom, far fewer seismic events were observed. So that's these red and orange dots. So you can see there are a lot more of these light blue and dark blue seismic events happening and far fewer red dots. And so why is that happening? So there's some seismic or some faults that are connected with the crystalline basin in this basement in this area, which isn't, because the perforations in the CCS1 were close to the basement, that induced, increased the pressure and kind of caused these seismic events to happen. But when they started injecting the CCS2, there's this mudstone baffle here, which separates the perforations in the CCS2 with the basement. And that mudstone baffle was sufficient to kind of minimize the pressure increase that the basement was seeing, which eventually minimized the seismicity that they were seeing at the surface. So that's just something to consider, when you're trying to find, when you have a zone that you're interested in, where in the zone you want to inject to minimize the seismic events. Because even though these seismic events were pretty minimal, lower on the Richter scale and probably not observable, you still don't want to have a project that has very frequent seismic events, just from a public perception. People may not want to have earthquakes around your project. I think in the past, you may have heard of this when in the middle of the 20 teens, they were injecting saltwater into disposal wells in Oklahoma, which caused a lot of seismic activity that was observable at the surface. And so because it was observable, they had to make some changes and reduce the injection to prevent that seismic activity. So it is something to consider. In the CCS1, they injected pretty close to the basement, which caused some of the existing fault networks to show some seismic activity at the surface. This just very small mudstone baffle in between the CCS2 perforations and the basement was enough to really drastically minimize the magnitude and the frequency of seismic events observed at surface. So on this slide, it's a picture of the Sleipner CCS project, which is probably one of the most successful projects that are currently running. So on the left here is kind of a picture of the Utsura sand that they're injecting in, with thickness on the color scale, and then this bar represents 50 kilometers, so you can see that it's 50 to 100 kilometers wide and several hundred kilometers long. So it's a very, very extensive, large, thick sandstone of very good quality. I think it's in the 1 to 2 Darcy permeability type of rock. Here on the right, you can see the Utsura formation that they're injecting in. What they're doing here is they're actually producing out of the deeper gas formation, and they have to extract the CO2 from the stream so they could get the gas to sail. So it's something that they were already having to do, and now they had this excess CO2 that they were trying to dispose of, and they are injecting in this Utsura formation. So this is a highly successful project. They have they have this natural gas formation. They have a really good sandstone that they're that is a shallower formation that they don't have to go too far to inject into. They're already separating the CO2 because they need to sell the gas to sail to get the sales quality. And the aquifer that they're injecting in is extremely thick, very extensive. So they've kind of got a lot of things going for them on this project. So this is kind of a case, like an ideal case study. To go a little bit deeper into this, you can see here on the left, this is kind of a log of the Utsura sand formation. So you can see it's very clean sand, very thick. In the middle slides, these are seismic that they shot to kind of track the movement of the CO2 with time. So this is 1994, 2001, all the way through to 2008, with the seismic kind of showing how the gas is being stored. And then here is kind of a 3D model, kind of showing you in 3D space how the gas is being, how the plume is kind of developing as you keep injecting the gas. A couple of things to note here. You can see that even though this is pretty clean section, you'll see that there's some really small type of lower quality rock or some sort of baffles. See, these aren't isolating or completely sealing, but they're just just a little stringers of lower permeability. And why this is really good is because if what's happening is when you inject the CO2 into the ground, as it starts moving up because it's lighter than water, it's hitting these little baffle surfaces and spreading out. And so what that's actually causing is that the CO2 is hitting even though it's one thick interval, it's hitting these mudstone or these lower permeability baffles and spreading out before going continuing vertically up through the section. And this is really kind of increasing the contact area that the CO2 sees, instead of it going straight vertically up if it was all vertically connected. So if the kVkH of that section was all one, what you'd expect is the carbon dioxide that was injected immediately starts moving vertically through the section and hitting until it hits your top seal, and then spreading out aerially. But what's happening here to their advantage is that it's hitting all these lower permeability stringers and then spreading out and also moving up vertically. So the amount of CO2 they can store goes up because they're accessing a lot more of the reservoir vertical space. So that's something that's also very kind of helpful in this case. So by this point, I mean, you should have a good idea on what type of attributes you're looking for in a reservoir for it to be a good candidate for CCS. There's some other things that may ultimately impact the amount of CO2 you can store. Like in this case, salinity can really impact what the eventual capacity is, how much CO2 gets dissolved in fresh water versus very salty aquifers. You can have minerals kind of form, CO2 reacting with the sands and the water itself. kind of mineralizing salts, dropping out salts or dissolving salts. So these type of things can happen in a project, but they're likely to not drive the reservoir selection. There's just things that you need to kind of keep in mind while you're injecting into the formation. The picture over here kind of illustrates the point that I was talking about earlier when we were talking about the Sleipner field. You can see here in the core on the right, the KVKH, the vertical, there's very little vertical heterogeneity. It's kind of a nice clean slab of sand. So you expect the vertical permeability and the horizontal permeability to be pretty close to each other. Whereas on the left side, you can kind of see these little stringers here that may reduce the vertical perm relative to the horizontal perm. And what's happening here is something that you saw in the previous slide, which is the CO2 is kind of more spread out a little bit here. So this is a cross-section from a simulation model, and the colors represent the CO2 saturation. And so the CO2 is migrating upwards, but it's kind of contacting a lot of the reservoir here. Whereas in this case, with the good vertical perm, it's immediately kind of going upwards and confining to a single layer because it doesn't have the opportunity to get slowed down by these little baffles that you would expect in a lower KVKH type of system. But anyway, these are all things to keep in mind, but ultimately, like it says here, ultimately less likely to drive the reservoir selection, but things to keep an eye on. So there are not too many carbon capture sequestration projects that are currently active. There are a lot in the pipeline, but they're not too many that are active, other than the ones that I kind of mentioned here. So that causes people to have to rely on simulation modeling to kind of understand where the CO2 plume is going to move, how much CO2 you can put into your reservoir, so you can come up with some estimates on, where's the plume going to travel to, how much CO2 you can ultimately sequester. And so in this picture here, on the right side, you can kind of see a screenshot of a plume, a model from a CCS project. So you can kind of see the concentration of CO2, and it kind of thins out as it gets further and further out. And this is really being used to determine what your area of the monitoring area that you need to kind of take into account when you have these type of projects. On the left here, this is just kind of showing you the fraction of the CO2 gas that's being injected, what portion of it is mobile or immobile or trapped or being dissolved into the water. After injection stops, you can kind of see that these fractions change with time as the CO2 in the mobile phase starts dissolving more into the aqueous phase. So you can kind of see this fraction of mobile gas starts reducing after injection stops. And then as the gas dissolves into the aquifer, it changes some of the properties of the fluid and can make it more dense, and it causes some complex movement of fluids, which is kind of harking back to the initial point of these type of projects rely heavily on simulation modeling to kind of capture all these type of physics that are happening as you inject CO2, and CO2 is dissolving and coming out of solution or going back into solution, getting trapped. So it's really heavily simulation dependent when you're trying to do this type of evaluations. Next slide. The next couple slides, and I know I'm kind of getting close to my time commitment here, so I'll try to go a little bit quicker. The next couple of slides just kind of go back to how simulation can be used to kind of change your area of review. So in this hypothetical case, and this is coming from the UIC Class 6 area review guidance from the EPA in the US. So this is just kind of a cartoon of these 3 injection wells. You have injection well 1, 2, and 3. And there's this old well that's kind of outside of what the initial estimate of where the plume will travel to was calculated from a model. So this is kind of pre-injection. This is kind of what they thought that the maximum extent of the CO2 plume would be. And let's see what happens on the next slide. So this is pre-injection. They start injecting, and their models initially predicted that the CO2 would be limited to these orange circles around the injection wells. But one of their monitoring wells started picking up some CO2. So obviously they need to kind of go back to their original pre-injection plume model and update it to be able to history match it and to calibrate it to this new data that they've received. So yeah, it says here, after 20 years, monitor well number 6 detects CO2 where it was not expected. So they go back and they update the model, and then the new model now brings this well into play. So it's just kind of an evolving process, right? You have this initial idea of what the plume is going to do when you're injecting into the ground. You have a monitoring plan, and you're observing how the plume is moving with time. And you feed that data back in to a reservoir simulator and then update it. And those updated models may cause you to have to change, what wells you're including in your monitoring plan. So it's kind of it's not a one and done type of exercise. You're constantly kind of updating, monitoring, recalibrating, and adjusting your CCS plan. You can use analytical evaluation. You can use analytical evaluations to kind of get an idea of how much CO2 you can put in the ground. So in depleted reservoirs, you can use material balance. If you have a good if you have a good data set on the historical, production and injection within an oil and gas reservoir through volumetrics and material balance, you be able to estimate fairly accurately how much CO2 you can put back into the ground. But there's some limitations to these type of methods, especially if you may not know if the land ownership is not a regular shape. you may not be able to put away all the volume that was produced. And again, like you've seen in previous slides, the reservoir heterogeneity can play a pretty significant role in how the plume migrates. So using material balance may not capture that aspect. So basically, coming back to simulation modeling, there are not too many of these analogs that are available and currently producing today. So you kind of have to rely heavily on simulation modeling to really come up with an idea on where the plume is going to go. This slide, it just kind of covering the SRMS system. It's very similar to the SPE's PRMS system, which we use for reserve reports all the time, except now that capacity is replacing the term reserves. They still need to be commercial, but one thing that I'd like to mention here of interest is the CCS project by itself doesn't have to be economic. It can be ring-fenced with some other revenue generating project. So for example, if you have an ethanol plant that's selling ethanol, and then you add CCS to it, you can, even though the act of capturing the CO2 and sequestering it underground may not be profitable, you could combine it with a more profitable revenue stream selling the ethanol and still consider it as economic. And the reason why I bring this up is a lot of companies and governments are all trying to get to this net zero target, and they may have all these ESG and net zero pledges that they want to achieve. So you can, there's at least it allows for the project to be combined with other revenue generating projects to be considered capacity or storage resources. So it doesn't have to be economic on its own. I think that's all the slides I had on CCS. But before I end it, I just wanted to put in a quick plug for some interesting and exciting developments that our petrophysicist team is coming up with. So our expert petrophysicist Jim Davidson and others have kind of put together a new a methodology for calculating the oil and gas, water, bitumen, and kerogen content in unconventional rock. They're going to be presenting this in the Unconventional Resources Technology Conference in Houston from June 20th to June 22nd. It's really exciting work that they've been working with in collaboration with Core Labs on for a better methodology, a better lab protocol for getting a better sense for the in-place oil, gas, water components. I'm not a petrophysicist, so I can't speak too much more to this, but just wanted to put that out there that this exciting work is coming out. And one more plug for our annual oil and gas property evaluation seminars. They're free to attend. They're typically targeted for non-technical financial professionals who work in the petroleum industry. So if you're interested, or if you know someone else who's interested in learning a little bit more about property evaluation or how to use a reserves report, these are free schools that we put on all over the world. I think we just wrapped up the one in Sao Paulo on May 24th. The next one's on June 28th in London, and Singapore in March of 2023. But they're fantastic schools that kind of go through and go from start to finish on the data that you use and how we integrate it into our property evaluations and how we run our economics. And it's really great if you're trying to understand what goes into our property evaluation. With that, I'll end it, and I can give back to Andrew, and we can take some questions if there are any. And thank you. Yes, I can. Yeah. That
okay. So my name's Angus. Saying I'm an imposter here because I'm a drilling engineer, but I have a question. I was interested to hear about these seismic activities associated with CO2 injection, and I'm wondering whether you envisage a knee-jerk reaction from NGOs, sort of trying to put a stop to CO2 injection as they have done with fracking.
Right. So that's a good question. I think, at least in the example that I had mentioned with the Archer Daniels Midland facility case study, the seismicity that they observed at the surface was very, very low. Like I said, it was 1 or 1.5, not nearly as high as what was being experienced in Oklahoma back in the 2010s when they're disposing salt water. So I think that just harkens back to picking the right sites for CCS to minimize the impact of seismicity. I can't really predict the future on what NGOs may do for preventing that seismic activity, but I think if you try to minimize it in the first go, then it's less likely that they're going to have impacts. The earthquakes in Oklahoma were being felt by people at the surface, and the 1.5s are hardly noticeable. So, as far as you can minimize it, I think that would be helpful.
Any other questions from the floor? I have a question.
Sure.
you hear lots of environmentalists say that there is no real successful injection or CCS program actually happening in the world. You've given me a couple of examples I'll go away and look at, but what is the success rate?
The success rate on injection projects currently?
Yeah.
Aside from so you saw the Sleipner field is very, very successful. The Insula project in Algeria is successful in the sense that they still put away CO2 for permanent sequestration, although they had that deformation at surface. So I mean, it still was successful, but it had some interesting learnings. I think there's a project that in offshore Australia. I think Chevron has a CCS project there. They're not having issues on the injection side. They're having issues on the pressure management side. If I remember correctly, I think it was a water production well that they were injecting into another formation that was kind of standing up. So it really wasn't the injection side as much as the pressure management side from the water producer. But there's, honestly, there's just not that many pure sequestration projects that have a lot of runtime. So it's a little bit hard to say what the success rate is just yet. But I think as there's going to be a lot more. There's a lot of interest, and it's only increasing year over year. So hopefully, as these projects get off the ground, we can get a better sense for how successful they are.
Okay, thanks. Any other questions? No? All right. We'll wrap up the meeting there. Thanks very much for your fantastic presentation.
Thank you. If there are any other follow-up questions feel free to contact me, and I'll chase down the answer. Yeah, sorry, I might have gone through those slides pretty quickly, but yeah, if there's anything at all, just feel free to contact me or anyone at NSAI, and we'll get back to you.
Thank you.
Thanks, guys.